Good. So today we will talk about coordination and clash detection, and basically focusing on 4D and 5D too. Okay. And the subjects are the federated model and coordination, and then automated clash detection, like hard versus soft. 4-dimensional BIM, which is the dimension for time, and 5-dimensional BIM, which is automated quantification and cost. Now, we will basically look into how we can integrate different disciplines, okay, multiple disciplines, into a single federated model, and based on that, how we'll detect the spatial conflicts. And then we have, of course, the dimensions of time and cost that we add to our BIM workflow. Coordination and clash detection is all about identifying physical intersections between different, let's say, discipline inputs, and also clearance violations. So sometimes we have these. And 4D is basically the time, and we basically add the schedule activities. Schedule is like, you know, the time list of different construction tasks, for instance, okay, to 3D geometry, so that we can visualize and simulate the construction sequence. And then 5D is costs. Basically, we have something called quantity takeoff. Quantity takeoff is basically when you employ the task of calculating how much material you need, how much money you need for a particular, let's say, construction activity. So this is what we call quantity takeoff. And we basically turn this into a dynamic model-based cost estimation with 5D. Okay? So yeah, here you can see in 3D we basically coordinate and resolve the clashes. We have automated clash detection, for instance. 4D is time, like how things come up, and 5D is basically monitoring the cost for construction. Okay? So let's start with federated model and coordination. Basically, we have this, like we have been talking about BIM, a model where people can contribute, etc. And one of the myths is that to have a single model, okay? So people think that, well, we will have a single model where people will be adding, removing things, but that's not the way it works. Okay, so this is basically this is a myth. Okay, so we cannot have a massive single large BIM model that can include everything. Okay, so for that, because it's impractical. Okay, because there is no software that can handle that much of data and run fluently. What we do is, and another thing is that if we combine architectural, structural, mechanical data into a single model, the end result will be a multi-gigabyte model, okay? And a multi-gigabyte model will not work. It's going to be slow, unwieldy, and prone to crash. Okay, so we don't want that. And of course, another thing is that managing the project roles. How are we going to manage who is adding something in and out? And how do we allow people to change things if we have a single model? Who is going to be the partner? Okay, so that's an issue, and that doesn't work because we can basically, if we do that, we will allow people to delete other people's work. Okay, so we cannot have a single model because that model will be bloated. Instead, we have many models, okay, and we have small models that come together. Okay, so that is the idea. So we will talk about that. This is what we call a federated model. Okay. So instead of a central file, we have a federated model where we have linked models. Okay, so we have distinct models which are linked to a single, let's say, space. So basically we have separate discipline models, but they are brought together in a federated model, okay? In that case, we have clear divisions of responsibility. So like an architectural model is under the supervision of architectural team. Structural model is under the structural team. Mechanical model is on the mechanical, or electrical model on the electrical. So basically each discipline can keep their intellectual property and design authorship. So you will not be able to change something that is done by a mechanical engineer, okay? So when we separate these models, basically each user can use their own separate software ecosystem, as long as they are compatible with what we do. Okay, so they use a specific software tool that is best suited for the discipline, and then they basically exchange the model with that federated model space. Okay, so this is how it works. So we have the architectural discipline, we have the, for instance, structural discipline, we have the mechanical, electrical, plumbing discipline. Okay, and these models come into this space. This is the federated model. So everything comes together, and then we can figure out what is going on, what is wrong. Okay. So as a result, we have a coordinated construction process. Okay. So this is the idea. Basically, we are trying to use this space to run our analysis. Okay. So discipline-specific authoring in that case is important because they work in their own native authoring environment. For instance, for architects, they may use ArchiCAD, they can use Revit, okay? But structural engineers, for instance, could use Tekla, okay? Or they can use other structural design software, structural elements-focused software. And basically, each model contains the elements that pertain to the specific discipline. For instance, a structural engineer, if they are dealing with the columns and beams only, and also the structural flooring, this is what that will be included in their model. Or if they are dealing with the pipes and plumbing, that's what is going to be included in their model. We will do some exercises about that after the midterm. Okay? So if a discipline, and basically they export version copies of their models. So we have different versions of the software of their models in their software. Okay? And if a discipline needs to see the rest of the building, basically they reference or link the other models. So like a mechanical engineer can bring the electrical engineer's work or architect's work. Architect's work is most of the times the thing that we base everything upon. Okay? So the most important one is the architectural model, and the other models basically can be linked into that model. Okay? But of course it depends. I mean, with some projects, it's different. Sometimes the structure is the most important thing. Architecture elements are added later. That's how it works, for instance. You can do that. Yeah, so basically, yeah, we have architect, we have structural engineer, and mechanical engineer. So they basically, as you can see, the structural engineer's work is here, the architect's work is there. So basically, they come together in a single environment. Okay, so that is the idea. And basically, how we do the assembly, in these specific BIM integration tools, we bring them together, okay? Like the Navis, we call these the coordination software, okay? Coordination software basically allows different people, different parties come together and look at these models together at the same time, and also figure out issues with them, okay, problems with them. Like we have this BIM coordination software like Navisworks, Manage, or Solidly Model Checker, okay, for the to form the federated model. These tools are very interesting. Now, as I told you at the beginning, to have a one single large model is difficult for software, but these software they bring only the essential information from the BIM models. Okay, this way they can manage large projects. Like Navisworks is like that. It's a very old software. I remember even in 2007, when I was in London, they were using it for a hospital project. And Navisworks at that time was a separate software that was built by some other company, and later Autodesk bought it, of course. You know, a big company, they buy all the relevant important software. They bought Navisworks. So Navisworks is amazing. It looks very bad. I mean, when you look at the model inside Navisworks, it's very simple. Like, it doesn't really have the detail that you can see in a regular BIM model. But well, we don't care. I mean, all we care is like bring things together and try to see what's going on, what's wrong. Okay. So yeah, they lock down the geometry so it cannot be edited during the review. The software, they handle large merge file sizes. Okay. And when they are brought together, basically we can see how the design team members works in 3D and 2D. So, like, this is the environment. In the BIM coordination environment, we bring together all these different software. So, for this, as I mentioned earlier, we use common data environment, okay, and CDE. Basically, CDE, in that case, for instance, is it could be Aconex. Okay, Aconex can also allow us to do that. It provides us a shared central platform for storing, exchanging models, plans, reports, other information. As you know, basically, we continuously move our information models from the native environment to this shared coordinating environment. Okay, and collaborative environment. Okay, so we basically deal with that, and we basically make sure that we have the latest or most recently approved models in that environment. So, as you remember, we talked about that in previous weeks extensively. So, let's go into this concept of automated clash detection. What is it? What is a clash? So, we talked about that. Basically, normally, before BIM, we were doing clash detection with translucent papers. Okay, so in the past, you would have the architectural model, you would have the structural model, you would have so drawings. I'm sorry, not models. You would have the architectural plan drawing on a translucent sheet. Then you would have the structural on a translucent sheet. You would have mechanical, and you would put them on top of each other. You would have different sections showing different elements. But you needed to understand how it works in 3D. And in reality, it would never work. You would always have issues. At least you would try to contain the columns in the right, locations, etc. But the little things like the pipes, etc., they would all get lost. You would be able to do that. So in the past, we used to do that with 2D drawings, but now we can do that in an automated manner, okay, with these BIM models that we have, 3D models. Yeah, traditionally we would do manually overlaying of these 2D drawings, but of course there are limitations, we cannot see well, and BIM software makes it automated because we can systematically identify geometric conflicts. Okay, if we have these 3D models. And we can prevent, why do we need that? Well, we want to know at the very early stages of the project so that we can fix the project. Because if you don't fix the project, when it goes to the construction site, changes are expensive. Okay, so they cost money. So, like bringing down bringing down a wall that is already constructed, it's painful, it costs money, and you don't want that. Happened to me, so that's how I know it happened to me. So yeah, it happens. So 2D BIM, 2D versus BIM, as you can see, this is how we did in the past. Putting things on top of each other, we would have a light box like the one that you had at the back. So we put things on top of each other, and we would try to figure out if things are clashing in 2D. Okay, with BIM, of course, it's all about visualizing it in 3D. So we have a federated 3D model, then we run automated clash detection, and we fix it virtually. So we basically we have this virtual rehearsal of the construction process. Okay? So, what is a hard clash? So we have hard clashes first. Hard clash is simple as two distinct building elements that are at the same time. You know, from physics, right? So two things cannot be at the same place at the same time. So you cannot have a column and a pipe at the same 3D location. So what do you need? We have to remove that, okay? Can you remove the column? No, you wouldn't. Column is more important, but a pipe can, you know, turn around the column. Or pipe can shift locations, go to somewhere else, okay? You cannot pass the pipe through the column, okay? Now, as a result, well, you will have the chance to fix it. On the construction site, you cannot put a hole in the column. Well, in Turkey they do, but you know, that's not true. That's not correct. That shouldn't be done, okay? Yeah, hard clash, a physical impossibility, okay? Like plumbing pipe running directly through a structural steel. And we can easily, automatically recognize these hard clashes, okay? And then we give the team to reroute the systems before this starts. So on-site improvisation is avoided. On-site improvisation is costly. It is not, it doesn't perform well, okay? It's bad, we don't want that. On-site improvisation. So, yeah, this is the clash. We have the beam, we have the pipe going through, we cannot do that. Well, this is one way of doing it, of course. Or we will find another, you know, location, but that's how it works. So we want to fix that. Soft clash is clearance and tolerance clash, okay? In soft clash, basically, for an element, we need a space, okay? And we need that space for maintenance, safety, or installation. I'll show you a clearance. Like if you look at the pipes above, they are about 10 centimeters away from the structural system. You see that? The pipes above. These were added later. These are awful, let me tell you first. But these were added with the space in between. You cannot basically design it so that the pipe is flush with the structural system. Okay, you need a space between. So that is what we call a clearance. Okay, and sometimes clearance is about, like in this case, it's about installation because these pipes have hangers. Do you see the hangers? Hangers are being connected to the structural system. You need a space to be able to put that hanger, you know, attach it, adjust it. It needs that clearance. Okay, so you cannot put things too close together. Okay, they are not intersecting physically, but they are too close. We don't want that. So another thing is that again, sometimes like you want to be able to access something, right? That box over there, you see that? That box. I mean, I want to control it, for instance. And consider that this is a fixed element, and I cannot open this, okay? So the box is there is space, but because of that panel, which is, let's say, fixed, okay, I cannot open the box. So this is another clearance. I cannot go in there. Like, I need to be able to squeeze it. And you need a space for a person, and you don't have that, okay? So this is, again, soft clash, clearance clash. So we need that, okay? So we basically, how do we do that? So when I design that box, okay, I create a transparent, translucent 3D volume around it, and I say that this box is on the wall, but you know, don't put anything close because you need this space for a person to be able to operate it. So I need to operate that box when I need to make changes inside. So we create translucent 3D volumes behind it. And then the software basically flags a clash. So if, like for that box, the translucent, for this circuit box, the translucent box is somewhere here. Okay? So it clashes with this. And that clash is flagged as a soft clash, a clearance clash, okay? Because it's translucent box intersecting with the panel, okay? So, yeah, this is how it works. As you can see, we have the air handling unit. No, I think it's a box where we need to access this door, but these pipes are going through this translucent box, which means that I'm not going to be able to open this cover. Okay? No, I cannot do it. So this is basically how it works. And I remember, again, 20 years ago in London, what they were doing was they didn't have that, and they had these people who were going through, in Navisworks, they were going through the B model, who were the facilities management people. They were checking every little thing manually at that time. Okay, 20 years ago, we didn't have that technology. But at that time, they were basically manually checking, okay, there's a valve there, I should be able to reach it, they would say, for instance. Is it blocked? Is it high? Is it low? Can I put a ladder to reach it? How does it work? Okay, so they were doing that visually in 3D. And of course, we have time and constructibility clashes. So this is another thing. See, the first one was hard clash. Second one is soft clash, clearance clash, and the third one is time and constructibility clash. Basically, conflicts in space and time, okay, across space and time. Basically, we are evaluating permanent structures against temporary construction elements. So what are they? Basically, temporary moving objects like tower cranes, delivery trucks, scaffolding. So, like, you're putting a scaffolding somewhere, and you want to know if you really can put it there at that time when the construction works. Okay, or if it blocks a passage, for instance. Okay, so basically we call these logical or constructibility clashes. Okay, again, these are the temporary static clashes, but then also we have logical and constructibility clashes, and these clashes are about the sequence of the work, like how do we basically safely do the work. Okay, like in time the crane works, but the boom of the crane hits the structure, for instance. So that's, well, this is a bad location for the crane, for instance, probably. So we have to be clear about that. Or we have to change the type of the crane. Okay? Or like you need a space for moving materials. Okay? In that case, you have a scaffolding and it's going to stop it. That's another clash. Okay? So these all change things. Then we have this thing called reactive versus proactive coordination. Now, reactive is, at the end of the day, we detect clashes after everything is designed. Okay? So we have, for instance, we have the architecture, design, structural, mechanical, electrical, and then we bring them together. We have also time. We bring them together and we figure out, oh, there's something wrong with architecture, we have to change that, oh, we have to do something about that. But, well, it's still good. I mean, because construction hasn't started yet. So you can, still benefit from that. But what would be better is to avoid that altogether at the very beginning. Okay? So if you could design where these clashes would basically be eliminated during the design, then you are in a better state. So you avoid clashes. So you result in federated models which are clash-free for the studs. Okay, so you want to do that. So this is what we call proactive approach. So basically, we have shared models, but we also, in these shared models, we allocate and reserve dedicated spatial zones for specific systems. Okay, so we say that, well, here I'll have these pipes for this large space. Don't put anything there, okay, so that we will not be fighting later. Okay, so we do that in networks, okay? And we use, and if there's a clash, we use something called beam collaboration format, BCF. And BCF is basically allow us to see the clash, basically setting up the view in such a way that it shows us in our authoring software where the clash is. Okay? So, yeah. Here, for instance, okay, we can say that, well, I will pass the heating, ventilation, air conditioning system. I think Yates designed this. So, yeah, this is a project from Yates' office, and they designed the space.
120 degrees.
Yeah. So the space is designed where we have the plumbing, we have the fire protection, electrical, and the space for all these are basically separate. Okay, and you basically know that you cannot put anything else there. Okay, so it works very. We call this reserved zones. Okay, reserved zones. So what kind of software do we have? I'll quickly go through them. We have desktop software, okay, like Navisworks. I hope we can try it. I don't know, we will see next after the midterm. So Navisworks is the most important one in the industry. Then we have Solibri Office. Navisworks is Autodesk. Solibri is Nemetschek. Nemetschek is like Graphisoft. Nemetschek also owns Graphisoft, a German company. They also own Graphisoft, ArchiCAD, etc. Right? So they have Solibri. Navisworks works with Revit, IFC, and they have a model, and it's very good. Nemetschek is an open bin software. Solibri. Nemetschek advocates open bin, IFC. We will talk about it next week. And there are political reasons behind it. But anyway, like Navisworks is from Autodesk. Autodesk prefers closed systems or systems that can work better with Autodesk and Autodesk ecosystem. Why? Well, it's all about marketing, right? Americans, they want to sell more, they want to meet us more, so, you know, that's how it works. But Solibri, Nemetschek, a German company, they are more about open. And why? Because they're a bit smaller, so they need some other software companies to be able to contribute. They prefer collaboration, that's why they prefer open systems. We have BIM Collab, Zoom, okay, BIM Collab ecosystem. So for BCS, this is a very industry standard tool, it's very good. We have Bexel Manager, and again, open BIM, 3D, 4D, 5D, 6D, so they are providing a very large, let's say, property set. Then we have Autodesk Construction Cloud, BIM Collaborate, okay? So we talked about the Construction Cloud in the past weeks. We have Redis 2, basically integrated collaboration platform. We have Triple Connect, we again talked about Triple Connect earlier. We have Dalux, and Dalux is quite good with augmented reality. So with Dalux you have these tablets and you walk around and then it overlays into the constructed space the elements that you want to see that will be constructed later, for instance. Then yes, we have USB Federation, which is an Akka software. I'm not very sure about that, and they work like that. So let's continue with the time dimension, 4D. Okay. So basically, we integrate project schedule, construction schedule into the 3D geometric model. As a result, the fourth dimension basically is the time. Okay. So the dimension of time is there to visualize the building sequence. Okay? So traditionally, we used to do that with Gantt charts or critical path method networks. So basically, we have these bar charts, which were manual, and you should be a very skilled or experienced person to be able to visually, let's say, three-dimensionally visually understand, you know, the implications of your charts. But with 4D BIM, basically 3D components turn into dynamic time-scaled simulations. Okay, so basically construction activities are represented with these 3D components. Okay, and basically with this we bridge the gap between design geometry and project management. So this is the most important thing. We have project management where they plan the construction activities, and we have the design model. So we want to be able to basically relate them to each other. Okay, so this is four-dimensional BIM. Like in the past, we were doing abstract Gantt charts. We still do that. They're important. You can still create Gantt charts, but you can also connect them to the model and create this 4D BIM where you can see different activities in time. Okay, and as a result, you can see what kind of clashes based on time can happen. Okay, so that's possible. So basically, we are able to visually simulate and evaluate the sequence. So we have this construction sequence that we want to figure out how it works before even, you know, starting digging the site. So we will be able to see that. This is what we call rehearsing, virtually rehearsing the project. Okay, so rehearsing. You know what rehearsing is? Like you do try runs. You're not doing actual construction. So we can identify constructivity clashes. Like sometimes one element blocks another element for the root, or one activity basically makes everything impossible to continue with. So that's what happens. And we basically decompose objects for that. For instance, if you have a single concrete deck which is very large, okay, you cannot pour it in one day. For instance, if it's going to be poured in several pieces, then you basically break it down to several pieces, split it into sections. Basically, it gives us a clear, intuitive communication. Okay, so between people. Basically, with the time frame, you agree on things with people. They can easily see the client, different contractors, different people, basically. Okay. There is another thing, of course. For instance, traffic. If you build in London, okay, you have to purchase the service of a traffic engineer. There is something called traffic engineer. Have you heard about it? Like structural engineer, you have traffic engineer. So traffic engineer goes to the site. Okay, so where is your site? Here. Okay, so on High Street, London. Okay, so High Street, London. This traffic engineer, many months before the construction, they go there. They count the number of cars passing through. They look at the pedestrian traffic through the day, through the weeks, through different times of the year. Then they basically make calculations, and then they say, well, for that site, you need to bring, you know, trucks, you need to bring cranes, etc. So the traffic will be intervened, right? So you basically provide a traffic management model. And in that case, you basically say that, well, I'm going to stop the traffic between 6 a.m. and 8 a.m. in the morning. I'll put these red lights, I'll put these people, and we will do everything, and it's going to be finished by 8 o'clock, so it's not going to impact the city, for instance. Or I'll do it overnight at these hours. I will reroute the traffic between here and there at this day, at this hour. I will protect the pedestrians. I'll let the pedestrians be able to go through underneath the construction site without being impacted. Okay, so you do all that. And for that, you need the 4D. Yeah, logistics, temporary works. Yeah, this is exactly what I was talking about. The temporary site elements and equipment can be logistically organized with that. Safely manage site access, optimize material delivery routes, spatial conflicts in highly congested urban sites. So you do that with BIM. With advanced 4D clash detection, you basically do all that. And also temporal conflicts, like if the mobile crane has enough physical clearance to maneuver around a new structural frame. Okay, so this is how it works. So yeah, the sweeping space for a crane is very critical. You should be able to lift the crane up in time for the construction. Okay, or the crane is like if there's another building nearby which is already there, existing, high, tall, and then you have to be taking care of that. So yeah, like here, where how the trucks will come, where will they load, what kind of materials they're bringing, how often. Even like in London, what they were doing was, which was very interesting. For instance, we call it just-in-time delivery. Okay, it comes from the automotive sector. Did you know, like when the cars are manufactured in the factories, the stock materials in the factory is nearly zero. So like when the car, I've seen it myself. I mean, I was in Berlin, Munich, in BMW factory. And the way it works is that each car, when they design the car, okay, the parts of the car are defined, right? So you have a steering wheel on the right, which is for Britain, for instance. You have, let's say, four-wheel drivetrain. You have this petrol engine. You have this skylight, leather interior, etc. So when you receive the order, you plan the manufacturing of that particular car to a particular time, and that time was, for instance, the day I was there. Okay, so on the serial production line, so the car parts are coming together, and this, for instance, you have this white or cream leather steering wheel. Okay, it's coming from the manufacturer, which is somewhere else in Germany, exactly on that day. And it's coming to the sites, factory, and the parts are coming into the line, and like the steering wheel is coming to the factory. I mean, I'm exaggerating not maybe in minutes, but maybe in a few hours, but not more than that. So the parts are coming from the other factory to the site and to the production line, and the workers are receiving them in boxes for that particular car. And I could see on the production, like there was this one blue car, red car, like also the robots, they're painting blue car, it goes, and then they paint a red car. It goes and they paint, like I always thought that they would do the same thing. No, the robots are changing paints even, like one after another. And then on the production line, you have one car which is hatchback, the other car which is sedan, with the other car which is like coupe, like it just works. And all parts are coming. One car is for America, it has different specs. One car is for Europe, it has different specs. And these parts are all coming in time. So we have the same thing in construction too. So in London, there are companies who do the procurement, or how do we call them? We have this something, there's a particular name for those companies. Just-in-time delivery companies. What they do is that for your project, okay, let's say that that day you are putting together the windows for the 4th floor, okay? So the 4th floor windows are packaged in that warehouse for that day. They have their own, scanning labels, etc. And then the 4th floor windows arrive to the site in the morning of that day, because you don't have space on site for the windows, okay? So it's delivered to the site in the morning, and that day then those windows are put in place. So just-in-time delivery for construction works great in congested city areas. Okay? And of course, trade coordination, safety planning. So like how do we make sure that different construction people work together in a fluent manner, okay? So we minimize interface problems in that case because we have congested workspaces. We have something called workspace definition too. Remember, I mentioned about the soft clash for this box, but that soft clash, that clearance clash was for operation. But for construction, we can create other workspaces too. Okay, so we can say that for this window, I have a space of like 2 meters from the window here, 2 meters to the out, where I'm not going to be able to let anyone in when I'm putting it in, okay? So if you define these workspaces, my professor in the US, her PhD thesis was about that, back in 1998, maybe, I don't know. The windows were defined with their workspaces, so construction activities were organized based on these workspaces. So you know that this person needs the space for that window, okay? So you need to be able to provide this. Also, we have safety. This is another thing. Safety hazards can be defined with the models. If you have an opening in the floor, that's a safety hazard, because you can basically put that, and you can identify and mitigate it. And one of my PhD students, he did work on that. So he was using eye tracking, virtual reality 3D goggles to figure out how the workers were interacting with hazards on construction sites. An ultimate game that we have is in the future is that we can design in BIM in a way that the construction process is less risky, or the risky areas are defined properly. Okay, so that is the idea. So yeah, we can also serve, we can use 4D animations as visual instructions to help people see the assembly sequence. I'll give you an example about that. When I graduated from the school, I went to Istanbul to work at a pipeline project. Ask me why, but I ended up there. Outskirts of Istanbul, I think Ömerli Barrage or something like that. And then they needed to build. I was dealing with the artworks, they called sanat yapıları, art structures. And art structure means like a little bridge under passage for the pipeline, okay? At that time I had hair like on my shoulders and like mustache and everything, and I looked like D'Artagnan, and they were calling me, oh, you are the postmodern architect who's going to design the underpasses for our pipeline. Yeah, I know that. So, and the design, the story is that the people who were going to build the formwork couldn't understand the design sometimes, okay, in 3D, because there were only plans and sections. So I was also given the task at the site to make physical models for the people, which would show them piece by piece how it's going to be built, and then they would understand, okay? So, but today, of course, with a 3D model, with 4D sequence, you won't even need that, okay? Yeah, so visualizing the trade harmony. So different trades should be working together in a way that they are not basically intervening with each other's work. Okay, so that's what we are trying to achieve. And of course, progress tracking, planned versus actual, like we want to see how we are doing, okay, on the construction site. We don't want to be too late. We don't want to be too let's say, taking too many risks. So we record the actual installation statuses on the site. We can transfer it back to the BIM software, and then we can compare the actual progress on site with the reality. Before, this was only done with Gantt charts. On the Gantt charts, we would have a regular Gantt chart, and we would have red pencils with the updated Gantt charts. So if the updated Gantt chart is becoming longer and longer, then you are in trouble, okay? But with the BIM model, you can basically in 3D, you can see what's going on, okay? So color-coded objects, for instance, can show how things are working or not. And this is what we call a visual real-time feedback loop. So we want the feedback from the site, okay? Yeah, like that. So the 3D model, we have the red alert, like there's something wrong, we need to fix it. We do that with site captured data. We use laser scanning. We use photos. We use notes. We use reports from online tools. There are many different ways, and these basically give us how the whole thing works, okay? And as a result, we want to say, well, we need more people to work for this task now to speed it up, for instance. We have to add more labor into it, or we want to add, then they might be saying, well, we need more concrete, well, we will buy it. We need more equipment, we will find it. But this is how it goes. So if things go slow, you want to speed it up, because when you're late, you pay penalties. You don't want to pay penalties, okay? So, what kind of software we are talking about for 4D? We've got Bentley Synchro 4D. Synchro basically brings the CPM schedules from, for instance, Primavera or Microsoft Project, and then combines it with 3D model. We used to have Synchro, I think, but I don't think we have the license anymore. Fusor, okay, again, real-time rendering 4D, 5D simulation engine. This makes it look even better. We have CM Builder, okay. If I'm not wrong, this used to be a software that was for project sites, but now they do BIM too. Empower Project BIM, again, another software which I'm not very sure, but again, they all do similar tasks, similar jobs. Okay, some are better, some are worse. So let's move into the last subject, the 5-dimensional BIM. 5D is, don't forget, it is the cost oriented quantification. So we basically extract in 5D BIM, extract the quantities from 3D models, okay, so that we eliminate the 2-dimensional quantity takeoffs, okay, manual quantity takeoffs. Did I tell you before? In the UK, there is a profession, again, for quantities too. It's called QS, quantity surveyor. So just like architects, civil engineers, facilities managers, that's another undergrad degree. We have quantity surveyors. Quantity surveyors are the people who deal with the finance of the project. They calculate the amount of materials, they calculate the labor, the money flow, everything. You need a quantity surveyor in that environment. In Turkey, we don't have it. In most of Europe, we don't have quantity surveys. In most cases, civil engineers do that task. They take over that task in Turkey. So yeah, to the manually following 2D areas and counting materials, it's not very efficient. It's basically, again, error prone, as we call it. It's error prone, it can create errors. So we don't want that. BIM is object oriented, so we can instantly query individual components for their sizes, lengths, areas, volumes, okay? And then cost estimation basically turns from manual counting of a static thing into a dynamic thing, dynamic data extraction. So we can focus on value analysis at the early stages, okay, and risk assessment. So instead of making all these calculations and make mistakes like I did, okay, you might be asking, you're a BIM professor, why do you do that? Well, don't ask me, okay. We're all human, and now you can basically bring out results nicely. Okay? So how do we do that? We basically link the extracted model quantities to external cost databases. So we can link to cost databases. These cost databases could be within our own company. If we are a big company, we can have our own cost databases. Or these could be commercial services. They give you prices for things. Okay? So we can basically create actionable financial data. So financial data that we can use to make decisions. Okay? So the BIM model itself is not enough. We basically use it to create model quantities and assembly names. Okay? Then from these we link them to external cost rules and databases. We can export the data directly into the software with plugins from, for instance, Revit, or we can use intermediary software formats like IFC, okay, file formats, or we can export directly to spreadsheets. We can create common separated values for CSVs, for instance. And we can also link them to the constantly updated online databases like something called RSVs, okay? And automatically see what's going on. So yeah, we have the model element, it's the intelligent 3D elements. Then we extract it to the central data hub, and then we connect it to RSVs, and it gives us the total price. That's as simple as that, okay? We can have conceptual or detailed estimation, okay? So what does this mean? The LOD impact, the accuracy and methodology that we use for 5D BIM changes based on the LOD, level of development, right? So if you have early schematic designs like LOD 100 or 200, you basically estimate based on parametric conceptual rules. For instance, you know, in Turkey we have such thing. If you ask some person, well, I'm going to build a villa, and then they ask how many square meters, you say like 200 square meters. And then they say, well, per square meter, you will be spending like 20,000 to 30,000 liras. Rough estimation, okay? In total, it's going to cost you like 4 million to 6 million. A rough estimation, okay? So, or like when you ask, then they ask you further questions. So, in this case, with LOD 100 or 200, you can have like cost per square foot or per, for instance, if it's a hospital, per hospital bed. More or less, they're roughly correct. But of course, you can make it cheaper, you can make it more expensive based on your choices of materials, choices of construction, you know, the location, etc. The time, that changes. And once you have LOD 300, 400, then we can have bottom-up estimating, which is basically estimating based on components. You can do that too, okay? And yeah, if there are no details, then we have the rough estimation based on experience, okay? You know, generic massing, rough costs. If we have LOD 300, we have better costs. If LOD 400, we have fabrication ready costs, like very, very accurate cost estimation. And again, target value design and real-time feedback. This is quite good. 5D allows us to give real-time feedback on finances. So this can start at the very early stages. Like you can say that, well, I'm going to build this for, okay? And then you can say that, well, I'm going to build it in steel. Then it can give you a rough estimate. Then you say, well, I'm going to build it in reinforced concrete, but with all glass, then it will give you another price. So basically, if you make changes, it can basically automatically tell you the final cost. This is what we call target value design. So based on the target value that you are, you know, aiming for, you make changes. You say, well, I'm going to make it shorter. I'm going to make it, let's say, cheaper by using different structural system or cladding, etc. Then it gives you that. This is what we call proactive, let's say, target value design. If we go for reactive value engineering cuts, that is damaging, because in that case, for instance, let's say that your ultimate aim is to create, like you have only 5 million liras, okay? And you want to create a very luxury restaurant, okay? All you want is a luxury restaurant. So, and you have 5 million liras. You can skip on, like at the beginning, if you put all these things together, it will tell you that, well, it's not going to be 5, it's going to be 6. Then it will ask you, what do you want to cut? Do you want to cut the size? Do you want to cut the luxury level? Do you want to cut the height, for instance, in the spaces? What is it? And how does it impact you? You make these decisions at the early stages. If you make these decisions at the later stages, for instance, you cannot change the size. You cannot change the height. You only have to cut down on the luxury part. And the luxury was maybe financially or in terms of trade, the luxury design was the most important thing to be able to bring customers, okay? Because there are many other restaurants which are similar with, you know, non-luxury features. And you, just because you wanted to keep it in 5 million liras, you don't have 6 million liras. You got rid of the luxury elements and then you fail. Okay, so it's just as simple as that. So you want to do that. And value engineering people, they will tell you, well, I mean, you cannot do luxury anymore. We already did the space and we have to cut down on the luxury pieces. So you don't want to do that. You basically go for target value. In this case, the value for you is the luxury. You say that, well, let it be small, but it should be luxurious. Okay, so that's what you say. Okay, as I'm not season also experiment on it, right? So, yeah, we continue with substitution of elements. We substitute different materials for different purposes, and you can see how the whole thing changes the end result. Okay, yeah. So we have this target budget gauge. This is of course symbolic, but you can see what changes when you change things, so that as a result you basically make sure that decisions are made properly. This is from the McLeamy curve. Don't forget McLeamy curve, the curve at the bottom right here. This is our ability to influence costs. In time, our ability to influence costs goes down. Okay, this is why. If you want a luxury restaurant, okay, you want to change the dimension of the space to keep the luxury level high at the early stage. You cannot change the dimension later. Okay, the whole thing will be gone. Yeah, estimator, in the past, estimators were continuously making takeoffs. This is what we call a rapid takeoff. So we quantity takeoff, and we make rapid takeoffs, okay? And we basically have to automate the process. BIM takeoff is not easy. Some people think that, well, I created the model, I will just put it in the software and it can give me the numbers immediately. It really doesn't work that way. You really need to work on it. And the estimator now needs to look into how to make that happen. And one of the most important things is standardization. For that, you have to have consistently named and classified elements in your project. What is a classification? Element classification. We have something called uniformat or master format. Uniformat is British, I guess. Master format is American. Basically, a hierarchical classification, categorization of building components. Okay, they have numbers, and in Turkey we have POS number. Construction sites practice this summer. We'll be dealing with POS numbers a lot. Okay, POS number in Turkish. But uniformat, master format are the most internationally renowned formats for classification. Yeah, estimators' role shifts from manual measures to analyzing construction assemblies. Okay, contextual cost based on building function, optimization of subcontractor pricing. Yeah, so the cost is now. What does this tell us? People are always afraid with the technology, right? So we always say that, well, the technology will come and we have all these estimators, they will be gone, they will be jobless. Not really, because they will have more work. It's not as simple as pushing a button. We still need estimators, and they need to learn this process, okay? This is why I'm telling you, I mean, in the field, you will be the managers of this process, and there are many job opportunities for you, okay? Your future is bright in that regard. Be positive and focus on learning, okay? BIM is your future in this case. What kind of commercial software do we have? We have something called RIB cost, RIB cost X, okay? We have Autodesk Assemble. I'm not going to go into details. We have Trimble VK Office. We talked about that. Nomitech cost us, I don't know what it is, but it's listed. We have Cubicost, and we have Primus IFC. Another feature for you is, I have some of my students who are in that field now. My earliest BIM students from 2013, some of them have started their own companies creating software. So we don't have a software, as far as I know, we don't have a reliable software in Turkey that can work with Turkish materials, Turkish way of construction, etc. So there are many, and also internationally, I mean, you can see I'm only talking about like 6 software packages. So if you come up with a good idea, start your designing your own software, you can have your own business. And I'm sure there will be someone who's going to buy your software. Okay? So look also into a future where you can write your own software. Okay? There are many opportunities there. You don't only have to be managers. You can be software designers too. Because the thing is, software engineers, they don't know anything about the needs. You will be the people who knows the needs. If you know the need, you're one step ahead. Okay, a software engineer who has no idea. My brother-in-law, he is a software engineer, and he's coming to me like, we want to do something, but we don't know what is needed. And I'm giving them ideas, and of course, most of the times, the ideas that I give them, we find out that it's already being done. So then we start looking for new ideas. But you know, well, we'll find someday. Hopefully, we will hit the gold mine. Good summary. Well, federated model. We bring together different disciplines and we make them work together. We know that we cannot have a single massive BIM file. A federated model basically links architectural, structural, and MEP models together. So we have distinct models, but we bring them together in federated model. So here we give a unified digital environment for all these people to work together and find what's going on. And we are doing that to reach proactive problem-solving collective, to reach a proactive problem-solving collective. Okay, so we don't want to work in isolated silos. Okay, so we don't want to work in isolated silos. We want to bring them together in a federated model. Okay, so this is the summary about federated model. Clash detection and risk mitigation is again a very important thing that we achieve with BIM. We can detect both hard clashes, basically physical intersections, and soft clashes, like clearance and tolerance violations with our 3D solid models. Okay, so we can do that. Basically, we can eliminate human cognitive errors, okay? And as a result, we virtually prevent expensive field rework, material waste, and schedule delays. Remember, at the early weeks, I talked about how construction sector is wasteful, how we are doing bad in terms of efficiency compared to other sectors. This is about it. And how I told you other sectors are doing well, like car manufacturing, and I gave you this today, the example of, for instance, BMW, right? In the factory, every part is coming from the suppliers just in time. You know how it works? They have like the BMW factory in Munich. They have suppliers from Izmir, okay? Izmir factory manufactures the cables for the car. We call them cable looms. They manufacture the cable looms for the car. And that car is a specific car that a customer ordered from the US just in time so that when they manufacture the loom, they put it in the truck drives to the border, goes to Germany, and when it's unloaded, the car is in the manufacturing line. Okay, so that cable directly goes to the car. So nothing spends time in warehouses or storage locations. The factory works in a lean manner. This is what we call lean manufacturing. Who invented that? Any guesses? Who could? Toyota. Japan. They invented the lean manufacturing, and construction industry took over that idea. We have what's called lean construction. Okay, so we want to build with elements coming just in time. This is what we call just-in-time delivery, JIT. Okay, so yeah, BIM helps a lot with just-in-time delivery. Virtual crashes, field successes, etc. And simulating construction, 4D, 5D, basically time, cost, we can visualize them and make life easier for everyone, okay? So that we can achieve a target design. This is the 4D and 5D. Good. Thank you very much. So, yeah, we are done for today's lecture. Any questions? The tutorial today is about, I think, internal partitions, internal elements, etc. If I'm not wrong, it's already online. Just do it, and we will continue. Okay? Good. Take care. I'll see you next week.